Welcome to this video on solving the differential equation for a simple harmonic oscillator. In this video we're going to take a look at where we left off in the last video where we had set up the differential equation and come up with a general solution, and now we're going to be more specific about what that general solution might include. So if you haven't checked that out, go ahead and check that one out so you know what's going on. I also have Desmos up here, desmos.com /calculator. This is their awesome graphing calculator that we're going to use to tailor our general solution. So just to put you back where we were, we had a block on the end of a spring and it was oscillating back and forth when we pulled it to one extreme. Now again, we're ignoring damping and energy losses just so we can build the most basic model and then we can develop it further. So over here I graphed the position as a function of time, velocity, and acceleration, and we came up with this second order differential equation which showed negative k over m, some constant, times the function x of t equals the second derivative of that function. And our general solution to that was a function that was x of t is somehow a cosine function. And now I'm going to put just some other constants in, our general constants, a cosine times b times t plus c. So I'm putting these general a, b, and c constants and coefficients in here so that we can tailor this function to a more specific answer and figure out a little bit more about it. Now, this, remember, is a physical situation, so when you feel like you're getting into the weeds and you might get lost, just think about this as a simple fact that it's a block just going back and forth on a spring. This graph, remember, shows where the block is at any given time, and so we know that it's reaching a maximum amplitude value here as time passes. So if we go over to Desmos and I adjust the A coefficient, I see that that adjusts the amplitude not only of the function, but also of the motion. So this would explain that if, say, this was 1.8 or even 2, that the block was moving between a maximum position of 2 and negative 2, passing through its equilibrium position. So we could say here that the constant A is in fact x maximum. It's the amplitude, the position amplitude, we should say. So the position amplitude will give us what A is. So let's go ahead and we'll slowly add to this equation. So we know that this is x sub m, and I'm just going to put an m instead of the whole term max, and I'm going to say x sub m times the cosine of b times t plus c. Okay, next up here we are going to look at what the b term does. Now, generically, in a function in trigonometry, if you will, this b is going to stretch and compress the function. Now, let's think of that in terms of what we've talked about. Well, a few videos back, we looked at the fact that from one amplitude through equilibrium to the other amplitude back through equilibrium, once I reach the same point again as where I started, that's considered to be one full cycle. So 2 pi radian cycle, and it can also be referred to as the length of time would be the period. So here in this function that I have, if I shorten it just a little bit, I could maybe get it to be exactly some value. So maybe 4 seconds. It takes the block 4 seconds to get back to where it was when I first started. So I know that this has something to do with the period, and I know that it has something to do with completing a 2 pi radian cycle. So let's take a look at what B could actually represent in this equation. Well, like we just described, it's showing how long it takes to do a 2 pi radian cycle. So it's not just the period, but it's actually going to be our term that we came up with before, which was 2 pi radians over t, which was known as the angular frequency. Now we will see that we can also write this just in terms of the linear frequency, but we'll get to that in a later video. So this is really 2 pi over t. So when I go ahead and rewrite this equation here, adding the next piece into the equation, I have x of t is equal to the maximum position amplitude times cosine times 2 pi over t times the time plus c. Okay, now at this point what we want to do here is take a look at what this actually also represented in terms of a variable, and we saw that we used this angular variable here, which is omega, lowercase omega, so I could actually change that even further to x of t equals x sub m times cosine times omega t plus c. Now last, let's take a look at what c affects in the function. Now this is where it gets kind of interesting, because if we shift the c value, we see that the function shifts left and right. So it has a horizontal shift to the function. Now we might think of that as what is the initial position of the object, because that is where the function is crossing on the axis. But it's a little bit more than that in this case of a trig function, because the function oscillates, right? And so one position is not necessarily the same as another in time, but is the same on the graph. And so what we refer to C as is the phase of the graph. Sometimes it's referred to as a phase angle or as a phase shift, but it's basically just showing at what point on the 2 pi radian cycle the graph is starting at. So that's how we want to think of it here, is what position on the 2 pi radian cycle is it occurring at, and we use the Greek letter phi to represent that. So it's not necessarily the starting position, but it's the phase of this, so that we're telling that information in terms of the radian. So for instance, if we started at 0 for the function versus if we started at, let's say, pi radians through the function, or 2 pi radians through the function, it would tell us where along the cycle it's starting. So it's not where it's starting at all, but just where it's starting within the 2 pi radian cycle. So when I write this in here, I have x of t is equal to x sub m times cosine of omega t plus phi. Now occasionally you'd also see a plus d written on here, and the d would just shift this whole function vertically up or down. So if we add this d here, we can see that you can shift this all the way up or down, but that really doesn't have much of a bearing on us in this particular equation. We could add that if we needed to, but it's self-referential within the function. Now if we look at this, we know from before that we showed that 2 pi over t, the angular frequency, was also equal to some sort of physical constant. And we showed that 2 pi over t was actually equal to the square root of k over m for the oscillating spring. So what we find here is that if we were to put this into the function, that we could actually have a function that looks something like this: x sub m times cosine of the square root of k over m times t plus phi. And this would tell us where the object is at any given time if this is the rate at which you are passing through the phase angle. So you could put in any time value and you could show where the object is at a given time. And we know that where it's going to be at any given time is dependent upon what the mass of this is, so how much resistance there is to its change in position, and also what the spring constant is, how strong this pulls with every stretch or compression. And so we have this function, which is a very cool and useful function. Now if you want to get into a little bit more theoretical detail here, you can see that a transcendental function or a trig function has to only have input values or output values of radians. And so if we took a look at all the units here, we would see that each coefficient that we added in the function here had a way to convert the seconds that we put as an input to radians and then back to meters using this amplitude. But that's just for the super math nerds out there like myself who really like to look at that in a lot more detail. The final thing we can do here is we can take the derivative of this function, and because we know that if we took the derivative of x with respect to time, we would get the velocity function. So we'll go ahead and do that. If you want, you can pause the video, try to figure it out yourself, but we'll take a look at it here in a second or two. So if you were to take your general form of this function, which we started with up here, where we have x of t is equal to a cosine times b times t plus c, if you were to take the derivative of this function, so if we did dx dt here, it would come out in the form of course, v of t, and that's going to give you negative a times this out here times the cosine of t plus c. And now obviously this is not going to be the same c value anymore, so maybe we could change it to being the phase shift of the new function. But let's go ahead here and take a look at what that might look like. So if we have x of t equals xm times cosine of, we're going to go ahead and do this here. I'm going to put omega back in here just to help us make this look a little bit simpler. So this is going to give me negative x sub m times omega times the cosine of omega t plus this phase. And now we can see what x sub m times omega actually equals. Well, if you think back to the equations that we have up here, we said that the amplitude now of the velocity equation is the velocity maximum value. So we could say here, if we put a little side note, that this negative x sub m times omega is actually the velocity maximum. That is equivalent to the velocity maximum, which I think is pretty cool. So when you go ahead and write this out, obviously the velocity function could be equal to this velocity max now instead of xm omega times the cosine of this phase of the angular frequency times t plus the phase. Now we could do this another time, go through and put the new function back in by going backwards a second time, and I just realized here that I put cosine instead of sine this whole time here with my values, so apologize for that. I need to fix that up here. Okay, so this was obviously going to be a sine function. There we go. Okay, so we have this sine function here, and that's describing the velocity maximum. Now the second time that we go ahead and we take the derivative of this function here, we're going to get a negative cosine function. We take the derivative of the velocity function with respect to time. So that's going to end up giving us a of t is equal to negative, and I'm going to go back to this expression here again, x sub m times omega. Now we're pulling it out again because we're taking this next derivative here, and we're going to be, it's a cosine function again, okay, times omega t plus this constant. And so what I see here has happened is I've actually come out with a of t is equal to negative x sub m times omega squared times cosine of omega t plus v. So again now, if we think of our graphs that we had before, the amplitude of this new graph is the maximum acceleration. And so we see here that negative x sub m times omega squared is the acceleration maximum. So there's another way for us to be able to establish that. The final thing that we're going to see in this explanation is that not only is this coefficient here have to do with angular frequency, but we can substitute back in root k over m for omega, and you can see how the K and the M values would affect the acceleration or the maximum acceleration, or how it would affect the maximum velocity. So that's a really cool thing that really puts this all together. Now in later videos what we'll take a look at is how to do this same process, setting up this differential equation, for other kinds of oscillators. So not only the spring oscillator, but also a pendulum oscillator, and then finally a physical pendulum. So a simple pendulum and then a physical pendulum. But we'll get to that later.